Imagine that you're sitting on a jury, and the case is a hit-and-run accident involving a taxi. And you live in a city that has two taxi companies. The blue taxi company, which runs 90% of the taxis in the city, and the green taxi company, which runs the other 10%. They helpfully paint their taxis accordingly. And a witness on the stand says that the taxi in the accident was green. But this accident occurred at night, and it was dark. It might have been hard to tell what the color actually was. So the witness was tested on his ability to tell the difference between the two colors of taxi under the same dark conditions. And he was pretty good at identifying both colors. He got it right 80% of the time for both green and blue taxis, and wrong the other 20% of the time. So which taxi company is responsible? We know you can't be 100% sure, but which color taxi is more likely, blue or green? If you're like most people, you'd say the green taxi company. We have a witness, and the witness is, more often than not, accurate. If you agree with this reasoning, you've just displayed a known bias called base rate neglect. That's when people take into account new information about a specific case, but they forget to take into account what's more broadly true, like the fact that there are far more blue taxis operating in the city. A base rate. A little bit of math can show what I mean. To make it easy, let's imagine there are 100 taxis operating in the city, and any one of them could have been involved in the accident. So that means there are 90 blue cabs the witness might have seen. And since he was right 80% of the time, it means he would have correctly identified 72 of them, but misidentified the other 18. Similarly, there were 10 green cabs the witness might have seen. His 80% accuracy means he would have correctly identified 8 of them, but been wrong on 2. So these are all the possible outcomes. What else do we know? We know the witness says the taxi was green. That means either he's right and he saw one of these 8, or he's wrong and he saw one of these 18 blue cabs that he would have likely misidentified. Against our intuitions, it's over twice as likely that he was wrong. So most people forget to take into account the base rates, the overall likelihood of seeing one taxi or another in a city, when they make a judgment about a specific case, like one person's likelihood of identifying the taxi. This math is an application of Bayes' rule, or Bayes' theorem. The equation associated with Thomas Bayes looks like this, but the idea here is much more simple. If you know the probability of one thing, and you know the probability of another thing that depends on that first thing, you multiply the two together if you want to know the overall probability of both those things happening. So what's the point? This is a bit of an unlikely scenario, but the math used in this case is identical to the math involved in judging the accuracy of tests for disease. There are healthy people in the population, like all the blue taxis, and there are unhealthy people like all the green taxis. And the test for the disease is like the witness. With a given test, we usually know the probability that it will correctly identify all the green car sick people and all the blue car healthy people. But we often also know how many people have the disease in the general population, equivalent to knowing how many green taxis are operating in the first place. Making the error of neglecting the base rate can lead to the conclusion of trusting the test, when in many cases it can be more likely that the test is wrong, even if it's accurate overall. And even doctors who should be experts in this kind of math can be prone to making this mistake. One study presented doctors with all the necessary information for a hypothetical disease, the base rate and the accuracy of the test, and then asked them to pick only which was more likely. Was the test right or was it wrong? 2/3 of doctors picked the incorrect answer. So what can we do about this? How can we avoid making this mistake? One possible solution comes from the frequency format hypothesis we've discussed previously. This is the idea that people generally understand numbers better if they're discussed as frequencies instead of probabilities. And some studies have found that fewer people will make the mistake of neglecting the base rate when you change the format. But a lot of those studies didn't just swap 90% for 90 out of 100 and 80% for 80 out of 100. They did the rest of the math for people too, like we did before. 80% became 72 out of 90, or 8 out of 10. So it might not be that the frequencies are easier to understand, it's just that the math is easier to understand once someone has already done it for you. A rule of thumb you can use is to look for the more extreme piece of data. The base rate suggests a 90% chance that the car was blue. The witness says it was green, but with 80% accuracy. If you only need to know which is more likely, trust the higher probability. In this case, the base rate of 90%. Once you do the math of applying Bayes' rule of conditional probability, you'll find that the more extreme piece of evidence will give you the more likely outcome. And now we begin the laboratory participation portion of the Know Your Bias series, in which we go out into the world and collect 100 cars, which will paint either blue or green. You can go with interior paint, it tends to be cheaper, and we don't need it to be durable. Then select one of those cars at random to hit an unsuspecting stranger in front of a...
You gotta cut that out. We can't run people.
I'm told this won't work. Don't do this.